I want to start by going through the quiz thing that you guys did. Hello. Thanks, dude. Paul, this is yours. You knew it was coming.
You got this, Paul. This is not Paul.
It's 9:50 now, though.
I was like, if you're okay with it, go out at 9:45. Because I gotta go into the room at 9:50.
I understand.
I
understand. All right. So these were the homework quiz questions that we did last time. It's my thought that every one of these could have appeared on a no calculator section of the multiple choice. Now, you guys, I think, used your calculators. I didn't tell you not to. There's no reason you shouldn't have. Will we do some no calculator stuff practice eventually? Yeah, but not like the first time we're doing something. But I want to go through and talk through how to do these things, assuming that you weren't using a calculator. So the first one should have been relatively easy. We're given this graph. It says, which of the following statements is false? F is continuous at A. I find A. I look at the function. It's like, well, I got to jump discontinuity there. That's already, that one's wrong. I peruse through. There's not like more than one answer possible. So I'm done. It just has to be A. I didn't bother even to read the other ones other than to check to make sure that like A and B or all of the above or something was a choice. But everybody cool with that? The next one, this is a squeeze theorem problem. Says, let f, g, and h be functions defined as f of x, yada, 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 for x not equal to 0. All the following inequalities are true on the interval from -1 to 0, or -1 to +1 for x not equal to 0. Which of the inequalities can be used with the squeeze theorem to find the limit as x approaches 0. So notice all in each of these, if I plug 0 in directly, we have indeterminate forms, right? We have something over 0. So first things first, let's check to see, just kind of go through one at a time on these. So if I plug -1 in, because that's the interval for x that I'm working on, I would end up with like -0.5 or something over -2, right? And sine of a negative is going to be a positive value, right? No, wait a minute. No, sine of negative becomes negative. Sorry. So that's going to be like a negative over a negative. But I know that sine close to 0 is going to be like a really small number. So this is going to be close to 0 at -1, right? Which should be less than a quarter. So I don't think that this is going to work. Do you guys see that? Okay. 2. Ooh, I like 2. This is like canonical squeeze theorem setup for me, right? Cosine is bounded between -1 and +1. I multiply the 1 or the x to the 4th to both sides. I get exactly this. I love this. That looks right on. So 2 is definitely one that works. The next one we'll look at here, if I plug -1 in for x, I'm going to end up with -1 on top. And tangent is negative on the bottom. Or on negative, tangent is negative when x is negative. So I'm going to have negative over negative. That's a positive. Okay, well that's maybe okay. If I do +1, I'm going to get the negative over, I'm going to get positive over positive. Well, maybe, but if I put in 1 there, or if I put in something, if I put 1 in there, this is close to 0. Or 1 degree or 1 radian is pretty is going to be close to there. You're probably getting something that's going to be, well, this is -1, right? This end here. if I plug -1 in to this, I'm going to have -1 over tan of 1. Tan of 1 is going to be less than 1, and between 0 and 1, excuse me, or 0 and -1, which means it's going to be something 1 over something that's a decimal is going to be big. So it's going to be too big for this, right? Now, did I have to rip out like what I remember about like what the graph of these things look like, or maybe the unit circle to kind of get some estimates going on? Yeah, I did. But the only one that would have worked is G, which thankfully is the only one that even looks like it's the canonical setup, right? In fact, tangent is not going to be easy to get a squeeze theorem for, because what are the natural bounds of tangent? The range for tangent? -infinity to +infinity. So it's not going to be a nice one. Hi, Katie. To deal with anyway. So next one, the limit as x approaches f of x, or a of f of x is equal to L, where L is a real number. Which of the following must be true? So basically, I'm going to try to draw a picture where the limit exists, but say, for example, f of a doesn't exist. So I could do something like that, right? That the limit exists at a, but f of a doesn't exist, right? So that doesn't have to be true. F of x is continuous at a. Well, the same example shows discontinuity. F of x is defined at a. Well, that's no, same thing as the problem. The f of a is equal to L. Well, no, f of a doesn't have to equal anything. So none of those things would be true in the picture that I drew of the limit existing. So I can conclude that it's none of the above. Everybody's cool with that? This one is a great theorems question. So the theorems that you would have needed was some of the continuity theorems, specifically like theorems like 5 and 9, I think, were from the textbook. But basically, what kind of function is I? Logarithmic, right? Logarithmic function is continuous over its entire domain. So all I need to check is 1 in the domain of the natural log? Yeah, natural logs are defined on all positive values. So continuous at 1, sure. What type of function is II? Exponential. Exponential is continuous over its entire domain, and its domain is all real numbers. So yeah, I got that one. Everybody's good there? III is a composition of an exponential and a logarithmic function. So I need to check if one is defined, or if the inside is defined at 1, or it's exponential on the inside, so it's continuous everywhere, so I'm good there. And then e to the 1 minus 1, I just need to check to make sure that's in the domain of the natural log, which it is, because e is like 2.7. So again, it's going to be a positive number. So I'm good. I got all 3 of them. Should have continuity. Everybody's okay with that? Again, haven't used my calculator. Haven't even really needed to use my calculator. All of this is prior knowledge and thinking about things the right way. Now, the continuity stuff, would I expect you to know all those continuity things like a day after we talked about it in class? No, but like illustrates to you how useful those continuity theorems are for doing anything, especially these multiple choice type questions where it's like, how would you do that without a calculator and not knowing that like those functions are, you know, given at you as continuous? It'd be tough, right? Be potentially a lot of work. So here it says f is continuous for this function, and when x is not equal to -2, we need to define -2 as So I noticed right away that that rational function is factorable, and that looks exactly like a removable discontinuity problem that we had seen in like our Algebra 2 class. So what's this thing going to look like? Looks like this, right? What it's asking us for is, okay, at -2, what value do I need to fill this in to make this thing now continuous? To fill in that removable discontinuity? I'm just going to plug -2 into this. And I'm done. Everybody's okay with that? Aside from the word continuity, that was almost an Algebra 2 problem, right? Okay. Here's just evaluating a limit. First idea would probably be to plug in or do a direct substitution. What's the problem? You get 0 over 0, right? So got to do something else. Hopefully looking at this, you notice that this is something that factors. So that reduces to x plus 3 over x plus 2. So I know that's the limit then is going to be the same as this limit. And now I can direct substitute that to get 5 over 4. The next one is a little bit tricky. So part 2 should be a jump right out to you as, okay, that I can factor and should be able to reduce. So when you do that, you get -x plus 4. So when you take the limit of that, then you get 1. So it ain't that. We have to look at these other two now. So if I look at the first one, I have the absolute value of x over x. But the key here is that the limit is approaching 0 from the left, which really means that what we have is like the limit as x approaches 0 from the left of -x over x. Why can I say that? Well, remember the piecewise definition for an absolute value function is that, right? Since we're operating over here, I can just drop the absolute value and replace it with that part of my absolute value definition. So that just gives me -1. So that one looks good. Everybody agree with that? And this one is exactly what we were doing in 2.6, I think, with the infinite limit down here. So what do you notice about the degree of the numerator and denominator? They're the same. So the limit then should just be the leading coefficient over leading coefficient. So it should be 1 and 3. Everybody's okay? All right. Here it says wants to find the limit as x approaches 1. What do you notice if you try direct substitution? Yeah, indeterminate again. So probably natural first step would be to try factoring this. And then you would have noticed either that I can rewrite that part as a difference of 2 squares, or maybe you decided to multiply by the conjugate. Either one is okay. because you're going to get to the same spot either way. Is that okay with you guys? Okay, here we're given a piecewise function where one of the pieces has this extra lurking variable here, this k in it, and we're asked to find the value of k that's going to make this thing continuous. So what's going on here, if I look at that first piece, that's going to be like, it's weird. It's going to do something like this, right? And it has that, oh yeah, that's filled, sorry. The second piece, what I want to do is I want to have it start right where that other one end, so that its open circle is at the same location as that filled in piece. Everybody okay with that? So what I need to do is figure out what this red point is. So it's 3 comma something. When I plug 3 in for x, I see that that's the point 311. So then I take this piece and I plug 3 in and say that has to equal 11. So k is -7. Everybody okay there? And then our last one here, I'm looking at the limit as x approaches pi over 4. If I look at this, when I see pi over 4 there, immediately I'm thinking that this is going to be a unit circle problem where I'm going to have to remember my unit circle values. If you tried plugging in pi over 4, what do you think is going to happen? Yeah, you do get 0 over 0. Now, it's easy to see you getting 0 over 0 on the top. On the bottom, it's a little bit trickier to see where that's going to come in. You have to do a little bit of yucky, like simplifying to get that to work. But what we'd want to do here is we're going to have to do some simplifying. And what I'm going to choose to use is a trig identity to do that. Specifically, I'm going to remember that 1 is the same thing as sine squared plus cosine squared. I'm going to write as cosine squared first. I now have like terms in my denominator. So if I combine those like terms, I get cosine squared minus sine squared. And that's great because that looks like a difference of 2 squares to me. And I should be able to factor and reduce everything now. Okay. If I use my unit circle, cosine of pi over 4, sine of pi over 4, they did me a little bit of favor there because what is the value for both of those? Yeah. So if I add those together, I get 2 root 2's over 2, which reduces down to just 1 over root 2. So just to illustrate to you, like all of these eminently doable with no calculator. Some of them trickier than others with no calculator, or required more like prior, stuff, theorems or definitions or whatever's, but all very doable with no calculator. We'll do some targeted no calculator practice here eventually, but not right away. I think the calculator is helpful in just kind of building some intuition up. Luke?
Will we ever have a class where we just sit down and do like a whole bunch of AP Calcs?
Mm-hmm. But probably more towards the end. Specifically the free response stuff, because that is often like mixing a bunch of topics. Like you're not going to find just limit stuff in a free response question. Yeah. It'll be like a whole bunch of different topics throughout the year, kind of all mushed together into one question. But towards the end, we'll specifically sit down and do some free response stuff in class. Most of the multiple choice practice, I'm going to just keep giving you like little doses, and towards once we get close to the test, maybe we'll do some, like I'll assign a full like multiple choice section for you guys to do as a homework or whatever. Like an old multiple choice test or whatever. Okie dokie. Let's take a minute and do some questions now. Does anybody have questions from homework? Blake?
Give me about a second to pull it up.
Okay.
Can you do number 31?
That was like a legit second. In what section?
It's going to be 2.6.
2.6, number 31. Okay. We hadn't seen the example yet that I would do in class that would be helpful to do this, but we can do it right now. All right. So what's the problem when if we tried to do like a direct substitution?
Negative infinity.
If I try to do that though, if I have a negative to the fourth power, that becomes positive. If I have a negative to the fifth power, that stays. So really if I tried to plug this in and do a direct substitution, I'd have infinity minus infinity. You guys agree with that? What's that equal? Not zero. It's one of the indeterminate forms. Remember, there's 6 indeterminate forms. Infinity minus infinity was one of them. Or 7 indeterminate forms, I guess. Okay? So infinity minus infinity is one of them. So that's just doing a direct substitution is no bueno there. So what I'm going to do instead is I'm going to try to turn this into a multiplication problem. I'm going to do that by factoring. So I notice I can take a greatest common factor of x to the fourth off. Cool there. And I know a limit of a product is the product of its limits. Okay there. Now if I do the limit as x approaches negative infinity of x to the fourth, I get positive infinity. And the limit as x approaches negative infinity of 1 plus x, I should get negative infinity. And if I multiply those together, I get negative infinity. Whoa! Very sneaky, Mr. Bullock. Blake, are you happy with what I did there? Yeah, quite sneaky though, right? Yeah. Amanda.
Can you do 27 for 2.6?
Same section, 2.7, okay, or 27, 2.6, okay. Oh, you didn't like the constants in this, did you?
Yeah.
Yeah, they just go along for the ride. So again, a direct substitution is not going to be helpful for me because I have all this stuff just kind of stuck in there, and it's just going to be like a bunch of infinities. What I'm going to try is to multiply by the conjugate. Going to give me x squared plus ax minus x squared plus bx over square root x squared plus ax plus x squared plus bx. And I notice then that I end up with ax minus bx on top. Oops, forgot my limit. Ax minus bx So far, so good. Okay. Now what I'm going to do is I'm going to multiply by 1 over x over the square root of 1 over x squared. Notice that this is still just 1 over x divided by 1 over x, right? Why did I write the denominator that way? Yeah, I got to multiply it into those square roots, so it has to be written with a square root on it. Okay. So that's going to be a minus b over square root of 1 plus a over x plus 1 plus b over x. And now when I take the limit of the numerator is just going to be a minus b, right? Those are constants as far as we're concerned because we're just worried about x approaching infinity. If I take the limit of the denominator, I would take the limit of the first square root separately. So when I do that, the limit of 1 is 1, and the limit of a over x is 0, because the x is in the denominator. Similarly here, so that's just going to simplify to a minus b over 2. That was a sneaky one, huh, Amanda?
Yeah.
Teagues.
Sorry, why did you change the a over x to a 0 and the b over x to 0?
So one of our theorems that we had was this.
Oh, yeah.
We had that theorem, so that's all I'm using there to do that. That looks familiar now. So again, the way I like to think about it is if I have a fraction and the bottom gets really big, what does that fraction go to? 0, right? Like 1/2 is 0.5, 1/3 is 0.3, 1/4 is 0.25. The bigger that denominator gets, just heading towards 0. Well, this one was going to be an issue because of the infinity in there, right? So until I got rid of the x's in the numerator and denominator, I was going to have an issue when I tried to do a substitution. So until I got to really this step where I got the x's out of either the numerator or the denominator, I was going to need to just keep kind of grinding at it. But at that step where I no longer have x's in the numerator, that's where I knew I could kind of stop and now start evaluating the limit. Does that make sense? Because I can't get infinity over infinity or infinity minus infinity. I don't want those things. Like, those are bad. I can't do anything with that. So I just have to keep grinding until I got the x's out of one or the other, because that gets rid of the possibility of getting infinity over infinity. Paul, did I see you had a hand earlier?
Yeah. See it real quick. Sorry about that.
That's okay.
2.5 number 11.
2.5 number 11. Okay.
I looked it up and kind of, as an explanation, I got it. But
Yeah, it says suppose f and g are continuous functions such that g of 2 is equal to 6, and the limit as x approaches 2 of 3 times f of x plus f of x times g of x is equal to 36, and it wants to find f of 2. So the key here is that f and g are continuous. Since they're continuous, I can just take this and do a direct substitution. And g of 2, we're told, is 6. So I have 3f of 2s plus 6f of 2s. That's 9f of 2s. And if I divide both sides by 9, f of 2 should be 4.
Okay, so you're just kind of treating like f of 2 as a variable.
Yep.
So.
Yep. That's all I would. That's exactly the way I would think about it. 100%. Is that cool? And the key piece was that f and g were continuous, and that allows me to just do a direct substitution. The continuity was the key there. If I don't have continuity, I could not make this assumption.
Cool.
Yeah, absolutely. Teagues.
55a and 2.5.
Yeah. I think the last class asked about this too. So this says prove the equation has at least one real root. When I'm basically being asked to prove the existence of a value like that, that screams intermediate value theorem to me. So the first thing I'm going to do is move everything onto one side and then define that as a function. Then we have to make sure that this function is continuous. And we know it's continuous because it's the difference of two continuous functions, a polynomial and a trig. if you're doing a problem like this on the AP exam and you omit showing that your function is continuous and you try to use the intermediate value theorem, you will not get full marks for that. You absolutely have to explain why the function you're using is continuous to be able to use the intermediate value theorem. That is part of a necessary condition to use it. Everybody's okay there? So now all I need to do is find a value of x that's negative, or that gives me a negative output, and a value of x that gives me a positive output, and that's all I need. So if I look at this, f of negative 1, I don't know cosine of negative 1 on my calculator, but that'll do. Oh, in fact, here, f of 0, that'll work. So that's 0 cubed minus cosine of 0, which is 0 minus 1, so that's negative 1. And then, so positive value, let's see, cosine of 3 pi over 2 is going to give me like 27 pi cubed over 8 minus cosine of 3 pi over 2. Well, I guess we'll write it this way. So 27 pi cubed over 8 minus a negative 1. That's positive. Okay? So I can say since f of 0 is less than or equal to 0, which is less than or equal to f of 3 pi over 2, there exists a c on the interval from 0 to 3 pi over 2 such that f of c is equal to 0, and probably I should have said by the intermediate value theorem. And that's it. Teagues?
Instead of 3 pi over 2, I use 1.
Yeah.
Would that work?
Yeah, as long as it gives you a positive value.
Yeah,
you're,
24 sections.
Yeah, that doesn't matter. Yep. I just picked something that I could do without the calculator. Tried to pick something. Right. I was going to use the calculator. I'm like, wait a minute, I don't even need to use the calculator for this. I can just pick a value that I can, unit circle value that I can deal with. But yeah, it doesn't matter. You know, you could have used like, you know, negative 10,000 and positive 10,000 and like should have worked out for you just fine. Like that's a big interval to search then afterwards, but it's not asking you to actually find the intercept. It just wants you to prove it exists. Or the 0, I should say. Same thing as an x-intercept, right? We use those terms interchangeably. Does that feel good though, Teagues?
Yeah.
So again, lots of options there for the intermediate value theorem. You don't need, you know, these two values that I used. There's nothing special about them other than one gave me a negative output and the other gave me a positive output. Any values of x would be fine as long as they did that. Anybody else? All righty. Well, let's finish up 2.6 then. So I think last time we were looking for the horizontal and vertical asymptotes for this function. And I think we were in the middle of doing this when we ran out of time. Does that look about right to you guys? So the HAs are the easy ones to do because we know what x needs to approach. And that's positive infinity and negative infinity. Is everybody okay here? Now, on the previous example, we multiplied here so that we would get rid of the the degrees, basically, right? So you could do the same thing here, or let's just shortcut this. What's the shortcut? I'm going to look at the degree of the numerator. What's the degree of the numerator, basically? It's degree 1. Why is it not 2? Because there's a square root over top of it. Good. And what's the degree of the denominator? Also 1. So this should be then just, since the degrees are equal, should be the leading coefficient of the numerator over the leading coefficient of the denominator. Now you could do all that extra mumbo jumbo that we just did, or that we set up, and kind of grind your way through that, like I did on that previous homework problem example. But I promise you, you're just going to get leading coefficient of the numerator over leading coefficient of the denominator. I'm going to do that, because that feels easier to me. Everybody's okay with that? Now, if I said to prove this, I would expect to see the algebra to work your way through to get that. But if it's just compute this, or what is the horizontal asymptote, saying it's this limit and the limit is equal to that, that's enough for me. The next piece we need to worry about are the vertical asymptotes. So the vertical asymptote can only appear or only occur when this function is undefined, right? So there's two things that could make this function undefined here. There's the square root and the division. Take a look at the square root piece. What's the domain if I look at just the square root piece? What's the domain of that piece? It's all real numbers is the domain. Why? Why can I plug a negative value of x in? Great, because the x is squared. Any positive x I plug or negative x I plug in gets turned positive, and then we can certainly take the square root of it. So there's no issues from the square root piece. The only issue I can have is from the denominator, right? So what value of x do I have to worry about there? 5/3. Now, I'm not going to be able to plug in 5/3 to evaluate this, right? Direct substitution is not going to be helpful here. And algebraically, there's nothing nice that I can do to do this algebraically. So I am just going to be using a table or whatever to do these. Or you can just kind of think about it. That's the way I'm going to do it. So if I plug in something that's a little less than 5/3, and I plug that into the numerator, I'm just going to get a positive number, right? Some normal size positive number. Everybody agree? If I plug in a little less than negative 5/3 into the denominator, I'm going to get a negative value that's very close to 0. Everybody agree with that? So if I have a negative value and the denominator is very close to 0, this is going towards negative infinity, right? As we get closer to 0 in the denominator, our numbers are getting bigger, right? 1/1 is 1, 1/2 is 2, 1/3 is 3. As those fractions get smaller, the whole thing, the denominator gets smaller, the whole thing gets bigger. Everybody's cool with the negative infinity came from? Again, you could use a table to evaluate that. There's nothing wrong with doing that. My suspicion would be something like this, that there's not an algebraic workaround on an AP exam they would give you. This would be a calculator active kind of problem. If I do the same thing where I go 5/3 from above, again, I plug into the numerator, I get a normal size positive number. I plug into the denominator, I'm going to get something, again, very close to 0, but positive. So I'm going to have a positive number divided by something very close to 0. So that should be positive infinity. Now, do I need both of these to show that I have a vertical asymptote? No, man, just one of them would be enough, right? Yes, sir.
And the first one is the numerator or the denominator.
Well, the negative is coming from the denominator, but it doesn't matter in a fraction where you want to put that negative sign, whether you want to put it in the numerator, denominator, out front of the fraction.
Right.
But it does come from the denominator.
Is a log, or is it negative, so it's positive?
Yeah, so basically you have positive over negative close to 0 is kind of what the fraction looks like there. But that's the same thing as just like, you can put that negative sign wherever you want, right? Like you put it out here.
Yeah.
Yep. Is that cool? Because you take something a little less than 5/3, you multiply it by 5 and subtract, or multiply it by 3 and subtract 5, you get something negative, right? Again, you could use a table to do this. You don't have to do what we just kind of talked through. But if it was a non-calculator active question, that's what you'd have to do, is just kind of like talk through it, because there isn't an algebraic workaround on something like this. You just have to kind of reason it out a little bit. Yes, Denise.
In like the class in general, or do you feel like you can't use your calculator on like
The class or the test that I'm going to give you in class?
Yeah.
Probably not. I haven't written the test yet, but I don't imagine I would do that for this first one. Would I, but like in the future, will we do stuff where we practice not calculator? Yes. I don't know that I would put it on like the test that I'm giving you. Like it seems like we can practice that in a lower stakes setting, right? We don't have to practice it on the test. You know what I mean? Since the majority of the practice you're doing is with your calculator, and that's the way it should be, right? I want you to use it, develop some intuition. Looking at the pictures is extremely helpful right now. But we'll do practice without it. Just don't think right away. Okay. Everybody's okay? I mean, goodness gracious, we haven't been in school a month. You're already talking about wanting to take away your calculator.
Oh, man.
I mean, you don't have to use it. You could try doing the test without it.
Okay.
My goal will be to write a test that I tell you can use your calculator on and have nobody actually open their calculator to do anything with it. Because it's just like, I can't do anything with any of these. Why are there's like that one Amanda asked about with the A's and the B's in there? It's like, what are you going to do with that? Not a lot with your calculator, right? You have to get pretty creative. All right. So I take a look at this example or set of examples. We're just going to go and we're just going to compute some limits here, practice doing this. If I try to do this direct substitution, what do I get?
You can't do a square root of infinity.
Well, it's if I do like infinity squared plus 1 is just infinity squared. Square root of infinity squared is like infinity. But what's infinity minus infinity? That's one of our indeterminates. So like, you have to do something else with this. What do you think we can try? Yeah, multiply by the conjugate. I heard somebody mumble it. That's what I think this screams, should be screaming at you, try multiplying by the conjugate. What part of this would be telling us that? That it has the square root, and then it's plus or minus something, right? That should be a pretty good indicator to us to at least want to try this. Now you got to do it right also. But what we found here is lovely, right? Everybody's okay here? Okay. What do you notice that we have here? Well, what's the degree of the denominator? 1. Right? What's the degree of the numerator? What's the degree of the numerator? 0. Because there's no x's. It's like 1x to the 0, right? Right? You can tack that onto the end of the constant, so it's degree 0. So what can we say then? That's correct. Why was I able to say this? This is true, right? That's basically what I have there. I have 1 over some x's down there. The x's have positive degree, going to 0. Everybody's cool with that? That's neat, right? Pretty neat. Okay, let's add in a little proposition here.
Can I get something out of the other proposition?
Oh, you're funny. The limit as x approaches negative infinity of e to the x should give us, what do you guys think? Should be 0. Right? Remember that a negative in the exponent is the same as making a reciprocal. So that limit would be like the same as the limit as x approaches positive infinity of 1 over e to the x. So you have 1 over big. That should be going to 0. You know, like sometimes that's enough, right? Like we get what we mean. Let's not get overly technical. 1 over big, that's 0. Right? Sometimes it just helps to make it simple. Calculus is complicated enough. If I can make it like 1 over big, that works. Okay. Let's do another here. So back to just computing some limits. It's like, whoa, Mr. Kulik, it's not an infinite limit. Well, this is the way you want to think about this. Oops. I'm going to think about this as a composition of two functions. And I know that the limit of the composition is equal to the composition of the limits. That I can smush the limit inside of the composition?
Is there supposed to be a limit in front of the Euler's number?
No.
Why?
So what I did is this. And I can do this because continuity. Everybody's okay? We see what I did now? And what is the limit as x approaches 0 from the left of 1 over x got to be? Negative infinity. So this could be then the same thing as the limit as x approaches negative infinity of, oh, I shouldn't say x anymore. I should say like some dummy variable like t. Okay, so let's just back up then a minute. Okay, so let's say t. Okay, how do I want to say this? Okay, so we know then. Let me use a different color. We know this is equal to negative infinity, right?
Right.
Okay. So what I'm going to do is I'm going to rewrite this original problem now. And instead of going to 0, I'm going to be going to negative infinity. And instead of using e to the 1 over x, I'm going to have like e to the t. So what this is saying here is, this is equivalent to saying the limit as t approaches negative infinity of t. Right? Because what's this limit evaluate out to? Negative infinity, right? That's going to be the same thing here, right? That's my negative infinity up there. And that's our proposition. Basically what I'm trying to do is build back that proposition, right? E to the negative x, or as x approaches negative infinity, e to the x goes to 0. I'm just trying to build that proposition back out with this.
Does it matter?
No, if it's, well, the e's not a variable. E's a constant. Yeah, I just picked t. Could be could be y, could be z, could be w, a, taco, chicken sandwich. I don't know, whatever variable you want to use. Who's hungry now? What if we have?
It's recorded. The lecture is recorded.
Yeah, it's recorded, man. What's the limit as x approaches infinity of x to the third? Infinity. Good. And what if I have same thing but going to negative infinity? Negative infinity.
So it could be that.
Nope.
If it was squared, it would be
If it was,
infinity.
if they were even exponents, both would be going to positive infinity.
Every time.
Whether it's, yeah. Because I know that like 3 negatives is still negative, right? So like the degree matters there. All right. What if we do then this? Can I direct sub this? No, because I'd end up with infinity minus infinity, right? What should I do instead? Yeah, the same trick that I did for Blake's question. We'll factor out an x.
Why can't you just subtract x squared by x?
Because they're not like
Sorry,
terms?
No, never, just disregard that.
Okay. Everybody's okay with what we did there? Now note that this is basically just a fraction or a rational function where the degree of the numerator is greater than the degree of the denominator. So yeah, of course that's going to go to either positive infinity or negative infinity. I remember that from algebra 1 or 2, or algebra 2, right? Let's look at one where it's maybe not quite so obvious. This will be, I think, my last example here in section 6. Can I direct substitute this? I just get infinity over infinity, and that's one of my indeterminate forms. Okay. So what do I want to try here? I mean, you could try that. It's not actually going to be helpful in this case, unfortunately. I'm going to do this. The reason I'm going to do this is because I want to get the x's out of the numerator or denominator, one or the other. Now, the denominator is only degree 1, so that's going to be the easier way to go. And in fact, you can't get the x's out of the numerator and do what you need to. Yes.
Is the degree in like that little fraction that we're multiplying by, is that always 1 less than the highest degree?
No, what I did is I wanted it to match the lower of the 2 degrees. So whether it was the numerator, denominator, whichever one had less, I'm going to use that one. At least in this case, where the degrees of the numerator is greater than the degree of the denominator. Everybody's okay with what I did there? Okay. So that, now I can split my limit between the numerator and the denominator. If I'm looking in the denominator, what's the limit as x approaches infinity of 3 over x? 0, right? 3 over big. And then What's the limit as x approaches infinity of -1? -1. Limit of a constant is the constant. And then what's the numerator? The limit as x approaches positive infinity of x plus 1. Yeah, just infinity, right? So what do I have here? Negative infinity.
Can I just say guess? I don't like a 1 out of 3 chance to get it right.
It's true. It's really, like, you don't have to get like 100, like a 100 AP test. You gotta get like a.
I have a proposition for you.
Okay.
If 2/3 of your class, like of the whole class, both classes get a 4 or higher, would you shave your beard?
That will not happen.
I don't want him to shave his beard. It's like.
When you
So
dye your beard,
iconic.
so
It is like, yeah. When you dye your beard. Yeah, when you dye your beard.
No.
Oh, yeah,
No.
Dude, right? Be Santa Claus.
It's only going to be like 2 more years. I'm going to be Santa Claus anyways. I don't need to rush that along here.
about dyeing your eyebrows.
No.
But like,
You
like
guys are
making your mustache more pronounced, like
you guys are weird.
wax the mustache.
It's
more
good motivation.
motivation.
Getting into college isn't enough.
So just to review what we've seen here. If the degrees are equal, then your limit's just going to be the leading coefficient over the leading coefficient. Thanks.
Are you saying yeah?
These are limits as x approaches infinity. Yep, this was the same thing that we saw in Algebra 2 when we talked about general rational functions, right? To define their end behaviors. Remember, this one was the slant asymptote situation where you had to do the polynomial division. That maybe rings a bell, maybe not. Yeah, right? Isn't it lovely when like you take something that was like, boy, that seemed really complicated, and you boil it down to like it's the same thing that you knew already?
It's like you don't have to stress, Mr. Cool, about shaving your beard. Because I have high hopes, but I don't know if 2/3 of the class is going to
No, it's so impossible as well.
No, I'm saying like
What about 2/3 of our class gets a 5?
Make it harder. What if 2/3 of the class gets a 6? Then I question: are we really in the right class if we are? Yes, Amanda.
I like this somewhere like above. Is that
Mhm.
for only like the limit of
It should be negative infinity as well. I think could still work. Yeah, that should be fine. All right. What do we have left? 10 minutes or something? Yeah. Okay. Let's do a little bit of 2-7 then. Don't huff at me. Cheapers creepers, guys. It's like you didn't sign up for the for this.
Bro, oh my lord.
Oh, no.
These are bad. Yes. That is bad.
Okay.
So
10 minutes left to class, guys.
2.7, we're going to start finally talking about derivatives. So there's two major operations in calculus, derivative and the integral. These are, most of first semester is going to be derivative. Most of second semester will be integral. We had this one little chapter of limits because it's part of the definition for each of them, but that's going to be spending a lot of time kind of building out the definition and then like all the little shortcut tricks we can use to do derivatives, and then like applications and like cool problems that you can use derivatives to solve, and it'll be like a whole thing. Bunch of theorems. All right, so we're going to go back to talking about the tangent line. So the derivative or the tangent to the curve y equals f of x at the point P is the line through P with slope limit as x approaches a of f of x minus f of a divided by x minus a. So write m equals. Okay, so this is, again, we kind of looked at this before. This is the tangent line at a point, or the slope of the tangent line at a point. So, little example. So let's say we want to find the equation of the tangent line to y equals x squared at the point 1, 1. To write the equation for a line, what do we need? 2 points or a 1 point and a slope. Which one do those two options you suppose we're going to take? 1 point and the slope. What's the 1 point? 1, 1. Right? We know that has to be on the tangent line. So all we need is the slope. So I'm just going to use what we did above. And we'll write it this way. So f of x is just x squared. Now notice here that I can't use direct substitution because we get an indeterminate form. But what can we do? Factor and reduce, right? X squared minus 1. Should recognize that as a difference of 2 squares. I'm going to take your silence as you were just too busy copying because I was writing too fast. Give you guys the benefit of the doubt. So when we do that, we get the slope is 2. Now we're going to write the equation for our tangent line. I'm going to use the point slope equation for a line. I think that's often the more convenient form when you have a point and a slope. So when I simplify that down, I have y equals 2x minus 1. Everybody's okay? The function's y equals x squared. Cool. Sometimes it's just an easy answer, right? So what about in general here then? So if we have y equals f of x, and we have some point P that's very close to f of x. So let's say I want to do the same thing. I want to write the equation for the tangent line to the curve y equals 3 over x that passes through the point 3, 1. This will be the last thing that we do here today. So again, just going to apply our new generalized definition. So when I do f of 3 plus h, that's going to give me 3 over 3 plus h minus f of 3 is just 1 and over h. Again, still indeterminate, because if I plug in, I get something over 0, right? So I'm going to make a common denominator in the numerator and hope that I can do some kind of simplifying here. And what do you see? Good things are a-happening, right? Everybody see where the negative sign came from? Be careful on that. And if I simplify this, I get negative 1 over 3 plus h. And then direct substitute gives me negative 1/3. So I do the point slope, and that gives me, when I simplify, negative 1/3 x plus 2. We're going to stop here. John.